Welcome to this coding tutorial. Today, we'll explore an interesting problem titled number 1468. Check if a string can break another string. We'll break down the problem, analyze different approaches, and discuss their complexities. Let's dive in. In this problem, you are given two strings, S1 and S2, both of the same length, and your task is to determine whether one string can break the other. Now, what does it mean for one string to break the other? If you reorder the characters of both strings, the reordered version of one string must have every character at each index be greater than or equal to the corresponding character of the other string at the same index. If this condition holds true, we say that one string breaks the other. The goal is to return true if either S1 can break S2 or S2 can break S1. Otherwise, you return false. The inputs to the problem are two strings made up of only lowercase English letters, and they will always have the same length. The output is a Boolean value indicating whether one string can break the other or not. Let's look at the first example. Here, S1 is ABC and S2 is Zaya. First, we reorder the strings to sort their characters. S1 becomes ABC, which is already sorted, and S2 becomes AXI, which is also sorted. Now, we compare the characters at each index. At index 0, A is greater than or equal to A, so that's true. At index 1, B is not greater than or equal to X, so that's false. Similarly, at index 2, C is not greater than or equal to Y, so again, that's false. Based on this, S1 cannot break S2. However, we also need to check the reverse comparison to see if S2 can break S1. When comparing in the reverse direction, we find that at index 0, A is less than or equal to A, which is true. At index 1, X is greater than or equal to B, which is also true. Finally, at index 2, Y is greater than or equal to C, which is true as well. This means that S2 can break S1, so the result for this example is true. In the second example, S1 is Abe and S2 is ACD. Sorting the strings gives us Abe and ACD, both already sorted. Comparing the characters at each index, we see that at index 0, A is greater than or equal to A, which is true. Next, at index 1, B is not greater than or equal to C, so that's false. At index 2, E is greater than or equal to D, so that's true. Because not all comparisons are true, S1 cannot break S2. Reversing the comparison, we check if S2 can break S1. At index 0, A is less than or equal to A, which is true. At index 1, C is greater than or equal to B, so that's true. However, at index 2, D is not greater than or equal to E, so that's false. Since neither string fully breaks the other, the output for this example is false. In the third example, S1 is LeetCode and S2 is interview. Sorting these strings gives us DLOT for S1 and INTER for S2. When comparing characters, we see that, at index 0, C is less than E, at index 1, D is less than E, at index 2, E is equal to D, at index 3, E is less than I. However, at later indices, some of S1's characters, like L, O, and T, are greater than their counterparts in S2. This means neither string fully breaks the other in this direction. But when comparing in the reverse direction, we discover that S2 can break S1. Therefore, the result for this example is true. Finally, let's consider some edge cases. First, if the strings have only one character each, such as S1 being A and S2 being B, the comparison is straightforward since there's only one pair of characters to evaluate. Next, if the strings are already sorted, like S1 being ABC and S2 being def, it simplifies the task since no reordering is needed. Another case is when both strings consist of the same character repeated, like AAA and AAA, where the result will always be true since every character is equal. Lastly, there are cases where neither string can break the other due to the distribution of characters, which is an important scenario to account for in your solution. To tackle this problem, let's start by considering two primary approaches. The first is the brute force approach. The intuition here is to generate all possible permutations of both strings, S1 and S2, and then check if any permutation of S1 can break any permutation of S2. While this approach aligns directly with the problem definition, it is highly inefficient. Generating permutations for a string involves factorial complexity, O(n), and when comparing all pairs of permutations, the overall time complexity becomes O(n). 2. This makes the brute force approach computationally impractical, even for small string lengths. While straightforward to understand, the trade-off here is that it is infeasible for real-world inputs due to its excessive time requirements. Now, moving to a more practical solution, we have the optimized approach using sorting. Instead of generating permutations, we can sort both strings and compare their characters directly. By sorting, we ensure that the characters are ordered in ascending order, allowing us to systematically check if one string consistently dominates the other. Specifically, if every character in the sorted version of one string is greater than or equal to the corresponding character in the sorted version of the other string, then the first string can break the second. The same logic can be applied in reverse to check if the second string can break the first. Sorting simplifies the comparison process, making this method much more efficient and feasible. Analyzing the complexity of the sorting approach, sorting each string takes log n time, where n is the length of the string. Once the strings are sorted, comparing their characters element by element is a simple O(n) operation. Combining these steps, the overall time complexity of this approach is log n, which is significantly more efficient than the brute force method. The space complexity is O(n), because we need additional space to store the sorted versions of the strings. This approach is not only efficient but also easy to implement, making it a practical option. However, it does require additional memory for sorting, which could be a minor trade-off in constrained environments. Another alternative to sorting is the character counting approach. Here, instead of sorting, we count the frequency of each character in both strings. Using these counts, we can determine if one string can break the other. By maintaining cumulative frequency counts, we check if the counts of one string consistently dominate the other. This eliminates the need for sorting, offering a simpler, linear time complexity for counting characters. Delving deeper into the character counting approach, the complexity analysis reveals that counting the frequencies of characters in both strings takes O(n) time. After obtaining these counts, comparing the dominance of one string over the other also takes O(n). Thus, the overall time complexity for this method is O(n). In terms of space, the approach is highly efficient with a space complexity of O(1), as we can use fixed-size arrays to store character frequencies, given that we are working with a limited character set. However, while this method is slightly more space-efficient than sorting, it comes with its own set of trade-offs. Specifically, it is less intuitive and more challenging to implement compared to the sorting approach. Additionally, this method may be less flexible when adapting to variations of the problem, making it less versatile overall. These limitations make it less favorable despite its optimal space and time complexity. Ultimately, we chose the optimized approach using sorting as the best solution for this problem. This strategy strikes an ideal balance between simplicity, efficiency, and clarity. Sorting both strings ensures that comparisons are direct and intuitive, which makes the implementation clean and easy to debug. While the character counting approach offers slightly better space efficiency, it is less straightforward and harder to extend for more complex scenarios. The brute force method, on the other hand, is dismissed outright due to its prohibitive time complexity. The main reasons for selecting this sorting approach include its alignment with the problem's requirements to compare characters after reordering, its efficient time complexity of O(n)log n, and its clear and concise implementation. These factors make it well suited for both coding interviews and production-grade solutions. In conclusion, the sorting-based approach is the most practical and effective strategy for solving this problem within the given constraints. To solve the problem, the first step is understanding the context. We are tasked with determining if one string can break another. This means that when both strings are sorted, every character in one string must be greater than or equal to the corresponding character in the other string. For example, if S1 can break S2, then after sorting, each character in S1 will either match or exceed the corresponding character in S2. Now, before diving into comparisons, we must validate the inputs. We check if the lengths of S1 and S2 are equal. If not, the problem setup is invalid, and we return false. Additionally, if either of the strings is empty, we also return false, as there's no meaningful way to perform comparisons in such cases. Once the inputs are validated, the next step is to sort both strings in ascending order. Sorting ensures that the characters in each string are lined up in a way that allows straightforward comparisons between corresponding positions. This is a crucial pre-processing step because it transforms the problem into a simple element-wise comparison task. For instance, if S1 is ABC and S2 is XYZ, sorting gives us sorted underscore S1 equals B, C, and sorted underscore S2 equals X, Y, Z. With this setup, we can efficiently compare characters between the strings. To facilitate this, we also initialize two Boolean flags, S1 underscore breaks underscore S2 and S2 underscore breaks underscore S1, both set to true. These flags keep track of whether one string can break the other. As we iterate through the characters, if we find that sorted underscore S1, I, is smaller than sorted underscore S2, I, we set S1 underscore breaks underscore S2 equals false. Similarly, if sorted underscore S2, I, is smaller than sorted underscore S1, I, we set S2 underscore breaks underscore S1 equals false. If both flags become false during the process, we can terminate early because it's clear that neither string can fully break the other. After completing the comparisons, we make a final decision based on the Boolean flags. If S1 underscore breaks underscore S2 remains true, it means every character in S1 was greater than or equal to its counterpart in S2, so we return true. Similarly, if S2 underscore breaks underscore S1 is true, it means S2 successfully breaks S1, and we also return true. If neither flag is true, it means neither string can break the other, and we return false. This approach highlights two key insights. First, sorting both strings as a pre-processing step significantly reduces the complexity of the problem. Instead of needing to evaluate all possible permutations, which could be computationally expensive, we reduce the comparison to O, n log n, where n is the string length. Second, using Boolean flags for early termination helps optimize the runtime further by stopping comparisons as soon as we know the outcome for certain inputs. Now, let's discuss edge cases to ensure our algorithm handles all scenarios correctly. For strings where all characters are equal, such as S1 equals AAA and S2 equals AAA, both flags should stay true because every character in S1 matches the corresponding character in S2. For strings where one is the reverse of the other, like S1 equals CBA and S2 equals ABC, sorting aligns them such that S1 can break S2. Lastly, consider completely non-overlapping strings, such as S1 equals XYZ and S2 equals ABC. After sorting, it's clear that every character in S1 exceeds its counterpart in S2, so S1 breaks S2. These examples demonstrate the effectiveness of sorting and Boolean flags in handling various input configurations. Additionally, the use of arrays to store the sorted strings ensures efficient element-wise comparison, while the Boolean flags simplify the decision-making process and allow for early termination. Let's walk through an example to see the algorithm in action. Suppose the input strings are S1 equals ABC and S2 equals Zaya. First, we sort both strings, resulting in sorted underscore S1 equals B, C, and sorted underscore S2 equals X, Y. Now, we compare corresponding characters. Starting with A and A, we see that A equals A, so S1 underscore breaks underscore S2 remains true. Moving to B and X, we find that B less than X, so we set S1 underscore breaks underscore S2 equals false. Finally, comparing C and Y, we see that C less than Y, confirming that S1 cannot break S2. On the other hand, for S2 underscore breaks underscore S1, all comparisons succeed, A equals A, X equals B, and Y equals C, so S2 underscore breaks underscore S1 remains true. Since S2 underscore breaks underscore S1 is true, the algorithm outputs true, indicating that S2 can break S1. This example illustrates how the algorithm systematically evaluates the strings step by step to reach the correct conclusion. This Python implementation solves LeetCode problem number 1468, check if a string can break another string. The task is to determine if one string can break the other as per the problem's definition. First, both input strings S1 and S2 are sorted to align their characters in ascending order. Sorting ensures that characters can be compared directly to determine the break relationship. Two flags, S1 underscore can underscore break underscore S2 and S2 underscore can underscore break underscore S1, are initialized to true. These flags track whether S1 can break S2 or vice versa. A loop iterates through the characters of both sorted strings simultaneously using the zip function. For each pair of characters, if a character from S1 is smaller than the corresponding character in S2, S1 cannot break S2, and the flag S1 underscore can underscore break underscore S2 is set to false. Similarly, if a character from S2 is smaller than the corresponding character in S1, S2 cannot break S1, and S2 underscore can underscore break underscore S1 is set to false. After the loop, the function returns true if either S1 underscore can underscore break underscore S2 or S2 underscore can underscore break underscore S1 is true, indicating that at least one string can break the other. This solution has a time complexity of O, n log n, due to the sorting step, where n is the length of the strings. Here, we begin implementing the solution in Java. First, we import the necessary utilities and define our solution class with the method checkIfCanBreak. The method takes two strings, S1 and S2, as input. Inside, we convert both strings into character arrays and sort them using the arrays.sort method. Sorting ensures that the characters in each string are arranged in ascending order, which allows us to directly compare corresponding characters to determine if one string can break the other. Next, we define two Boolean flags, S1 can break S2 and S2 can break S1. Initially, both are set to true. These flags will help us track whether S1 can break S2 or vice versa as we iterate through the characters of the sorted arrays. The core comparison happens in the for loop, where we iterate through each character of the arrays. If at any index a character in S1 array is smaller than its counterpart in S2 array, we set S1 can break S2 to false because S1 fails to dominate at that position. Similarly, if a character in S2 array is less than the corresponding character in S1 array, we set S2 can break S1 to false. This logic ensures that we only allow a break condition if one string consistently dominates the other across all characters. Finally, after the loop completes, we return the result of S1 can break S2, S2 can break S1. This means the method will return true if at least one of the flags remains true, indicating that one string can break the other. If neither flag is true, the method will return false, meaning no break condition is satisfied. This implementation leverages the sorted arrays to simplify the comparison process, ensuring that the solution is both efficient and easy to understand. The concise structure of this approach makes it straightforward to determine whether the given strings satisfy the breaking condition. To solve this problem, we start by sorting both strings. For the example where S1 is ABC and S2 is Zaya, sorting them gives S1 underscore sorted as B, C, and S2 underscore sorted as X, Y. Next, we initialize two flags, S1 underscore can underscore break underscore S2 and S2 underscore can underscore break underscore S1, both set to true initially. These flags will help us track whether one string can consistently break the other. Now, we compare the characters from the sorted strings one by one. Comparing it from both strings, since they are equal, no flag changes. Then we compare B from S1 underscore sorted with X from S2 underscore sorted. Here, B is less than X, so we set S1 underscore can underscore break underscore S2 to false. Lastly, comparing C with Y, C is still less than Y, but since S1 underscore can underscore break underscore S2 is already false, there's no further change. At the end, S1 underscore can underscore break underscore S2 is false and S2 underscore can underscore break underscore S1 remains true, which means S2 can break S1. Therefore, we return true. In this example, we have S1 as Abe and S2 as ACD. Sorting both strings results in S1 underscore sorted as B, E, and S2 underscore sorted as C, D. Again, we start with both flags, S1 underscore can underscore break underscore S2 and S2 underscore can underscore break underscore S1, initialized to true. First, we compare A from both strings, and since they are equal, there's no change in the flags. Next, we compare B from S1 underscore sorted with C from S2 underscore sorted. Here, B is less than C, so we set S1 underscore can underscore break underscore S2 to false. Finally, comparing E with D, E is greater than D, which causes S2 underscore can underscore break underscore S1 to be set to false. At this point, both flags are false, meaning neither string can break the other. Therefore, the result of this example is false. Here, S1 is ZYX and S2 is WVU. After sorting, we get S1 underscore sorted as X, Y, Z, and S2 underscore sorted as U, V, W. With both flags, s1 underscore can underscore break underscore s2 and s2 underscore can underscore break underscore s1, initialized to true, we begin comparing the characters. First, x from s1 underscore sorted is greater than u from s2 underscore sorted, so we set s2 underscore can underscore break underscore s1 to false. Then, comparing y with v, again y is greater than v, but since s2 underscore can underscore break underscore s1 is already false, the flag remains unchanged. Lastly, comparing z with w, z is still greater than w, and there's no further change. At the end, s1 underscore can underscore break underscore s2 is true and s2 underscore can underscore break underscore s1 is false, meaning s1 can break s2. Thus, the result for this example is true. When analyzing the time complexity of this solution, we start with the sorting step. Both input strings, s1 and s2, are sorted individually using Python's sorted function. Sorting a string of length n involves a complexity of O n asterisk log n, and since we sort two strings, this step contributes O n asterisk log n plus O n asterisk log n, which simplifies to O n asterisk log n. Next, after the strings are sorted, the algorithm iterates through their characters using the zip function. This character-by-character comparison is a single pass over the length of the strings, which adds an O n overhead. However, since sorting dominates the runtime, the overall time complexity of this solution is O n asterisk log n. Now, turning to space complexity, the major factor here is the creation of sorted copies of the input strings. When we sort s1 and s2, we generate two new lists, s1 underscore sorted and s2 underscore sorted, each requiring O n space where n is the length of the strings. Together, this adds up to O n plus O n, or simply O n. Additionally, the algorithm uses a constant amount of auxiliary space for variables such as the Boolean flags and the loop iterators, which is negligible compared to the space required for the sorted copies. Therefore, the overall space complexity of the solution is O n. To better understand the efficiency of this approach, let's consider the best, average, and worst case scenarios. In the best case, the strings might already be sorted or have an order that allows one to break the other early. However, since sorting is always required, the time complexity remains O n asterisk log n. For the average case, the algorithm still performs sorting and iterates through all characters, maintaining the same O n asterisk log n time complexity. Similarly, the worst case involves sorting both strings and fully iterating through all characters, so the complexity does not change. Comparing this with a brute force approach, the naive solution would involve generating all permutations of one string to compare them with the other, which has an infeasible complexity of O n. By leveraging sorting and a single comparison pass, the optimized approach achieves a manageable O n asterisk log n time complexity. To mathematically verify the big O complexity, we see that sorting each string requires O n asterisk log n operations, as sorting is based on comparison-based algorithms like timsort. After sorting, iterating through the characters contributes an additional O n complexity. Since O n asterisk log n dominates O n, the overall time complexity becomes O n asterisk log n. For space complexity, the sorted copies of the strings take O n space, while auxiliary variables use only O 1 additional space. Therefore, the total space complexity is O n. This analysis confirms that the solution is both time efficient and space efficient for the problem at hand. One common mistake when approaching this problem is mixing up the order of constraints. For instance, it's crucial to remember that if S1 is supposed to break S2, this must hold for all characters after sorting, not just some. Misunderstanding this can lead to incorrect results, especially in edge cases like strings with repeated characters. Another frequent issue is overlooking edge cases entirely. Examples include failing to handle empty strings, strings of unequal lengths, or strings with special characters. For example, if the lengths of S1 and S2 differ, the solution should immediately return false, but missing this check can cause unexpected behavior. Additionally, inefficiencies often arise when sorting both strings repeatedly during comparisons. Sorting should ideally be done once, as repeated sorting can unnecessarily increase the time complexity to O n asterisk log n within a loop. Lastly, some candidates attempt permutation-based solutions. Generating all permutations has an exponential time complexity, making it impractical for larger inputs, so this approach should generally be avoided. Another source of confusion is misunderstanding what it means for one string to break another. Some mistakenly think that breaking is determined by the sum of ASCII values in the strings, whereas the correct approach is to compare characters one by one after sorting. Recognizing this distinction is key to solving the problem correctly. A helpful pattern in problems like this is to reduce complexity by sorting the strings and comparing them lexicographically. Sorting up front in O, n asterisk log, n, and then performing a single pass comparison in O, n, is often the most efficient strategy. During interviews, clarifying edge cases with your interviewer can save you from misunderstandings. For example, you might ask if empty strings are valid inputs or whether the strings are guaranteed to have the same length. Finally, writing test cases is critical. Cover a variety of scenarios, such as small examples like ABC and XYZ, medium ones like AB and ABAB, and edge cases like strings of unequal lengths to ensure your solution works in all situations. This problem also shares similarities with several other LeetCode problems. For example, problem 242, valid anagram, involves comparing two strings after sorting them, which uses a similar technique. Problem 452, minimum number of arrows to burst balloons, applies sorting and greedy strategies, which parallel the character comparison process here. Another related problem is problem 937, reorder data in log files, where you sort based on custom conditions, much like the breaking constraints in this problem. Lastly, problem 179, largest number, relies on sorting with custom comparison logic, which is another variation of the breaking condition. These problems demonstrate how understanding sorting and comparison techniques can help you tackle a range of challenges beyond just this specific problem. When considering alternative approaches, the brute force method involves generating all permutations of S1 and comparing them with all permutations of S2. While this might work for very small strings, it's highly inefficient due to its factorial time complexity, O, n. For larger strings, this approach becomes infeasible. A more optimal solution involves sorting both strings and comparing them character by character. This has a time complexity of O, n asterisk log, n, and is generally efficient, though sorting might not be ideal in scenarios with strict real-time constraints. Another alternative is to count character frequencies using an array or hash map, such as an array of size 26 for lowercase alphabets. This approach has linear time complexity, O, n, but is only applicable when the character set is small and predefined. Each method has trade-offs, so it's important to choose the approach that balances efficiency and the problem's constraints. Great work! We've summarized the key points, discussed the algorithm, and analyzed its complexity. Remember to practice this type of problem to strengthen your sorting and comparison skills. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!